Hi everyone. So we are looking at section 2.5 today. This is the last section in chapter 2. And as you can see, we are talking about multiple angle and product to sum formulas. So we're actually going to be studying basically 4 different categories of trigonometric identities in this section. So of course, we're starting out with our first category, which would be the functions of multiple angles. So multiple angles, of course, we're talking about functions such as sine of k times u or cosine of k times u. Then for the second category, we'll be talking about squares of trigonometric functions. So that would be something like sine squared of u. Okay. Then for the third category, we are looking at functions of half angles. So that would be sine u divided by 2 for an example. And then of course the last one would be products of trigonometric functions. So something like sine of u being multiplied with cosine of u. Okay. So the first thing we're actually starting out with is the double angle formulas. So these formulas are pretty commonly used, of course, in trigonometry, but also in calculus. Now, if you go to your textbook page for section 2.5, you can actually click on this little link over here for proofs in mathematics. Okay, so this is where you will be able to see your proofs for, of course, we have the sum and difference formulas from the last section, but as you scroll down, you will see the proofs for your double angle formulas, for your power reducing formula, sum to product formulas. If you just wanted to come and kind of look at these proofs, it's kind of neat. They show you how they came up with these formulas and stuff like that. So you can take a look at it if you like. Okay, so let's go back over here. And so these are going to be your double angle formula rules over here. So you can kind of follow these along. Now for the cosine of 2u function, depending on what function you are looking at and how you want to solve it, you can actually use any one of these substitutions to kind of help you out. So they can actually break this down in 3 different ways. Of course, you only have one rule for sine of 2u and one rule of tangent of 2u. Okay, so let's see how we can use these formulas over here. So our first example is talking about solving 2 cosine of x plus sine of 2x equals 0. So they are basically saying begin by writing your equation so that it involves trigonometric functions of only x, which means you want to get rid of this 2x that we have with our sine function, and then we can factor and solve it. So what's happening over here for sine of 2x? We are using this double angle formula and rewriting it as 2 sine of x times 2 cosine of x. Okay, and then what's happening here is between both of these functions, cosine of x and cosine of x is common. 2 and 2 is common, so we bring out that 2 and cosine of x, and you are left behind with 1 plus sine of x. And of course, this is your factoring. Then you take each factor, set it equal to 0, and you can figure out what values of x you can come up with. And of course, this is specific to the interval in 0 to 2 pi, but if we're going to do these as general solutions, then again, both cosine and sine function have a period of 2 pi, so you add 2 and pi to your answers, again, where n would be your integer, right? So that's kind of the idea behind these, this example right over here. So let's take a look at our example. We are given cosine of 2x plus cosine of x equals 0. So let's see how we can break this guy down. So here we have this guy. So of course you can see for this first part over here, cosine of 2x, we again want to go ahead and write that as an angle just in terms of x. So we are going to use our double angle formula over here, and we are actually going to use this form. right over here, 2 times cosine squared of u minus 1. Now you can try with the other ones, but I think it gets more complicated with those. So this second form is going to be the more direct route for us. So we'll go ahead and rewrite this one as 2 cosine squared of x minus 1, and then bring down that plus cosine of x, okay? And then of course we want to try and see if we can combine any like terms or try to factor this. I'm going to rearrange this. I will have 2 cosine squared of x in the front. I'm going to take this positive cosine of x and put it in the middle, and minus 1 at the end. So I'm actually giving this a quadratic form. And if you give it a quadratic form, then you can easily try and factor it. So if we say, okay, let u equal cosine of x, then you can have 2 times u squared plus u minus 1 equal 0. So you're basically looking to factor this, and this will factor into 2u for the first term, u for the last term, and then of course this will factor into -1 here and +1 here. And it might be some trial and error for you to figure this out, but you will see this is the combination that will end up working. And then we can come back to our problem and rewrite this as 2 times cosine of x minus 1 for our first factor, and the second one of course will be cosine of x plus 1, and then everything equal to 0. Okay, so we'll go ahead and factor this, and then of course take each factor, set it equal to 0, and then get your cosine of x function by itself. So we'll start by adding 1 over here. Then of course you want to get rid of that 2, so divide both sides by 2, and we end up getting cosine of x equals 1/2. Okay, and then on the other side we will just subtract the 1, and this will end up giving us cosine of x equals -1. So again, go back to your unit circle, and you can try and figure out where cosine of x is going to be 1/2. So cosine of x equals 1/2 is going to happen at right here, pi over 3. And of course those are positive 1/2, right? And looks like the only other position is going to be right here at 5 pi over 3. So pi over 3 and 5 pi over 3. And then for the other side we have cosine of x equals -1. So cosine of x equals -1 happens right here at pi, right? So this will happen for x equals pi. Now just to translate this into your general solution, because they did not ask us to find this specifically in 0 to 2 pi. So that would be your x would be pi over 3 plus 2n pi, right? X would be 5 pi over 3 plus 2n pi, and then for the last one, x would be pi plus 2n pi, and we would say where n is an integer. Okay, so that would be your solution to this example 1. Okay. Now let's take a look at a different type of example here. So they're asking us to evaluate functions involving double angles. So we are given cosine of theta equals 5 over 13. and your angle theta is between 3 pi halves and 2 pi halves, so that's of course a quadrant 4 angle, right? And they're asking us based on this condition to find sine of 2 theta, cosine of 2 theta, and tangent of 2 theta. So the first thing we're actually going to do, we know this is a quadrant 4 angle, and they're telling us cosine is 5 over 13. So if you just think of this as being our little right triangle, then this distance here becomes 5. Of course, your hypotenuse, or you can think of this as the radius, becomes 13. So if you find the missing side, this side ends up being 12, but because it's on the negative side, you can call that as negative 12. So that's why they're getting this ordered pair of 5 and negative 12. Your x distance is going to be 5 units. The y distance is going to be negative 12, right? And then based on that, they are basically finding the sine of theta and tangent of theta. So this is your side r, this is your side x, and this is your side y. So that's the definition they're using, which we had seen in chapter 1. So you've got negative 12 over 13, negative 12 over 5, just by this figure. Now, we were asked to find sine of 2 theta, cosine of 2 theta, and tangent of 2 theta. So you are using those double angled definitions over here, and then just substituting in for your sine of theta, cosine of theta, tangent of theta based on these numbers that I have over here, and you can then simplify your answers and come up with your answers that way. Okay, so we have a similar example to that with us here. We are given sine of theta equals 3/5, and this is going to be between 0 and pi halves our theta, so that is of course a quadrant 1 angle, right? And we're finding sine of 2 theta, cosine of 2 theta, and tangent of 2 theta also. So let's see what our example would end up looking like. So the first thing we want to do is go ahead and create a little triangle for ourselves. Okay. So this is an angle, sorry, quadrant 1 angle. So you can imagine, you can do a little triangle if you like, and this is going to be our angle theta. So sine is opposite over hypotenuse, right? So based on that, you can use your Pythagorean Theorem and calculate your missing side, right? So which will come out to be 4. So 4 will be your x value, 3 will be your y value, and of course 5 will be the r value if you want to use those formulas. So we already are given sine of theta equals 3/5. Okay, and then cosine of theta, again you can do based on angle theta, would be adjacent over hypotenuse, or x over r, which will end up giving us 4/5. And then in that same way we can get tangent of theta, which will be y over x, or opposite over adjacent, which will be 3/4, right? So we can come up with those 3 angles, and then to find our sine of 2 theta, we are going to use our double angle formula. So double angle formula for sine of 2 theta would be 2 times sine of theta multiplied with cosine of theta. So that of course comes out to be 2 times sine of theta was 3/5, right? You can see that above right here. And then cosine of theta was 4/5. So that will end up giving us, if you think of this guy as being 2/1, 2 times 3 times 4 will of course end up giving us 24, right? You can see 2 times 3 is 6, 6 times 4 is 24, and denominator would of course be 5 times 5 times 1, so that's going to be 24/25. So for sine of 2 theta, this is the answer we're going to come up with. For cosine of 2 theta, again, it's really up to you which formula you want to use for the cosine function, but I think I'm actually going to use cosine squared of theta minus sine squared of theta, and you can use any of the other definitions also, so it's really up to you. They should all work equally well. So again, we know cosine of theta is 4/5, so that's going to be 4/5 to the second power, minus sine of theta is 3/5, so that's going to be 3/5 to the second power, which will of course end up giving us, I'm not sure why this keeps doing that. So this will give us 16/25 minus 9/25. So same denominator, right? So you just have to do 16 minus 9, which will end up giving you 7/25. So that's going to be the value for our cosine 2 theta right there. And then the very last thing we have to find is our tangent of 2 theta. And this formula is 2 times tangent theta divided by 1 minus tangent squared theta. Okay? So 2 times tangent theta is 3/4. So that's our numerator. Then on the denominator we have 1 minus tangent squared theta. So that will be 3/4 squared. Again, on the numerator, you can think of this guy as being 2/1. You can either reduce that fraction or you can keep it as it is. It is going to end up reducing eventually. So if you want to just keep it for now, that will be 2 times 3, which is 6. 4 times 1, which is 4. On the denominator, we will have 1 minus 3 times 3 is 9. 4 4s are 16, right? Now, just on the denominator, we do want to go ahead and combine those two terms. So you have 1 minus 9/16. We can go ahead and find a common denominator here. And you can end up getting 16 minus 9/16, keeping our numerator value the same for now. You will end up getting 6/4 over, again 16 minus 9 will be 7, so that will become 7/16. So we are dividing 6/4 by 7/16, so you can basically invert that second fraction and make it 16/7, right? And then reduce your fraction at this point if you like. So 4 will go into itself once, 4 goes into 16 4 times, and of course nothing else will cancel out. So 6 times 4 will give you 24, 7 times 1 will give you 7, and this will be our answer for tangent of 2 theta. So you can see it's really not that bad. You're given sine of theta initially. Draw your little right triangle in quadrant 1 because that's where your theta is going to be. Come up with your cosine and tangent functions, and then using those double angle formulas, we are able to come up with the value for these 3 functions. Okay, so that was our example 2 over here. Now they're talking about double angle formulas are not restricted only to angles that are 2 theta and theta. You can have other double combinations. So you can break these down with 4 theta and 2 theta. You can also do these double angle formulas with 6 theta and 3 theta. So you can basically see if you are given sine of 4 theta, this 2 in the front will stay the same, but now your angles will become sine of 2 theta, cosine of 2 theta. Same thing with the cosine of 6 theta. You can actually rewrite these as cosine squared of 3 theta minus sine squared of 3 theta. So by using double angle formulas and of course the sum and difference formulas that we had seen in section 2.4, you can actually use those formulas also to kind of help you come up with other multiple angle formulas. So there's so many different ways that you can go with these identities here basically. Alrighty, so let's go ahead and take a look at example 3 over here. They're asking us to rewrite the trigonometric function sine of 3x only in terms of sine of x. So they don't want us to have that multiple angle anymore. So we're taking sine of 3x and rewriting it as 2x plus 1x or 2x plus x, right? And then you're basically going to be using your sum formula, which was from section 2.4. So let me actually show you that really quickly. They're using this formula right over here to rewrite the expression here in our example 3. So sine of u cosine v plus cosine u sine of v. And that's what we have here. So sine of 2x cosine of x plus cosine of 2x sine of x. Okay? And then for sine of 2x, they are using your double angle formula over here. This cosine of x is the same from the above. And then for cosine of 2x, they are again using the double angle formula and rewriting it as parentheses 1 minus 2 sine squared of x. And then of course this sine of x stays the same. They are taking the sine of x and distributing it inside the parentheses. Multiplying the cosine with cosine to get cosine of squared. So that's how they're cleaning this up. And then in the very last one here for the cosine squared of x, they're actually using a Pythagorean identity to write this all in terms of sine of x, because they asked us, right, to write everything in terms of sine of x. So we're substituting for cosine squared of x by using the Pythagorean identity here. All of these terms are now only in sine of x, and they actually again went back and distributed this guy over here, and then combining your like terms, this is going to clean up in your answer. So it can be a little time consuming, because you have to remember all the different formulas you can use, all the different identities you can use. So it might not be a bad idea to kind of keep these different formulas and identities handy when you're working through these examples. So we have a very similar example to that here, where they're asking us to rewrite cosine of 3x in terms of cosine of x. Okay, so let's go ahead and take a look at that. So this is example 3 for us here. So just like you saw, we can go ahead and rewrite cosine of 3x as cosine of 2x plus x, right? So we will go ahead and use again the sum formula for the cosine function. So the sum formula for the cosine function is this one here. Cosine u cosine v minus sine u sine v, right? So this guy will be rewritten as cosine of 2x cosine of x minus sine of 2x and sine of x. Okay, then using our double angle formulas, we are going to rewrite cosine of 2x, and we are going to rewrite sine of 2x. Okay, so for now I'm going to put this in parentheses for cosine of 2x, and again we need all our terms to be only in cosine of x. So I'm actually going to use this substitution here, which is 2 times cosine squared of x minus 1, and then bring down this cosine of x. We have a minus sign there. And then we need to rewrite sine of 2x. So again, using our double angle formula, that's going to be 2 sine of x cosine of x, and then bring down that last sine of x term. So in parentheses is where we are just rewriting cosine of 2x and sine of 2x by using our double angle formulas from page 1 of our 2.5 section. Okay, now what we're going to do is go ahead and take this cosine of x and distribute it inside our parentheses. So that will end up giving us 2 times, it's cosine to the second power multiplied with cosine of x. So that will become cosine to the third power, and then negative 1 times cosine of x will be negative cosine of x. I am also going to take the sine of x on this side and multiply with this parentheses. So again, our minus sign. 2 sine of x times sine of x will become sine squared of x. And then, of course, we are left with cosine of x over here. Okay? Now, since we have this sine squared of x still left behind, and of course we don't want the sine function in there, we want all of these to be the cosine function, this is where we're going to bring our trigonometry identity, which is actually going to be, remember your Pythagorean identity, sine squared plus cosine squared of x equals 1. So if you take your cosine squared to the other side, you will have 1 minus cosine squared of x. So that's the rule I'm going to use in here. So let's go ahead and write down everything else that we have. So that's 2 times cosine cubed of x minus cosine of x minus 2. And now for the sine squared of x, I'm going to replace this with 1 minus cosine squared of x, and then your last cosine of x will come down. So using this identity that I just wrote down here in green, I'm using that to substitute. Now, here's going to be the interesting part. You can actually think of this as being 2 cosine of x, right? So both of these actually need to be distributed inside the parentheses. So again, I'm going to go ahead and write down my first part. And then I am multiplying negative 2 cosine of x times 1. So I'm taking negative 2 and this cosine, multiplying it with 1, which will end up giving me negative 2 cosine of x. And then negative times negative will become a positive here. So we're doing 2 times cosine of x times cosine squared. So that will basically be cosine squared times cosine, which will be cosine to the third power. And then you can combine your like terms. So these guys will be like terms, and then these guys will be like terms. So 2 cosine cubed of x and 2 cosine cubed of x will of course become 4 cosine cubed of x. And then minus cosine of x minus 2 cosine of x will of course become minus 3 cosine of x. So this is what they wanted, our function to be only in terms of cosine of x. Now this 4 cosine cubed of x just is telling you it's cosine of x is raised to the third power, right? But it is still in terms of cosine of x. So this is what they wanted us to do. So as you can see, at each step, we had to either use a double angle formula, or we had to use a Pythagorean identity, and then we had to use just basic algebraic techniques of, distributing our functions and stuff like that. So you can kind of see how these examples work out, okay? Alrighty, so that was our problem number 3. Now the next set of examples we want to get into are the power reducing formulas. And again, you're actually using the double angle formulas to come up with these power reducing formulas. But now we have sine squared of u. So since this is to the second power, we are now breaking it down into just first degree functions. So sine squared of u, you of course get 1 minus cosine of 2u divided by 2. Cosine squared of u will become 1 plus cosine of 2u over 2. And then of course your tangent squared of u is 1 minus cosine of 2u divided by 1 plus cosine of u, which is no surprise because tangent is always going to be sine squared over cosine squared. So that's why you're getting 1 minus cosine of 2u from here, and you're getting 1 plus cosine of 2u from here, okay? Alright, so again, you can go to your textbook page if you want to see the proofs of how they came up with these formulas. So this example here, as you can see, is a typical example you would end up seeing in a calculus course. So they are talking about rewriting sine to the fourth power of x in the first powers of the cosine of multiple angles. Okay? So when they are saying it can be cosine of multiple angles, they are basically saying it can be in terms of cosine of k times u. Or in this case, you can think of it as being cosine of k times x, since they're writing these in terms of x. So you can see we're actually taking our fourth power and breaking it down into the second power. So it's basically taking x to the fourth power and rewriting it as x squared to the second power. So that's what they're doing here. Sine squared of x raised to the second power. And then for sine squared of x, they are using this power reducing formula over here. So they're writing it as 1 minus cosine of 2x over 2. They took the denominator because that would be 2 times 2, which is 4. So they're taking it outside as 1/4. And they did a FOIL on the numerator, which gave you this parentheses part. And then they are using, again, the power reducing formula over here, which is what gives us the 1 plus cosine of 4x over 2. And then, of course, what they did here was they went ahead and distributed this 1/4 inside the parentheses. And they're just trying to clean this up as much as they can, combine like terms, clean it up. And then from each term, they took out this 1/8 as a common factor, and then whatever you were left behind with went inside the parentheses. Okay? And again, the graph is just showing you if you took this original sine of sine to the fourth power of x and graphed that, and you took this last part that we just came up with and graphed that also, your two graphs are going to be exactly the same. So this is to show you that both sides of your equation are also going to be exactly the same. Do not worry about the graphing portion. You are not required to do that. So our example is pretty similar to that one. We are given tangent to the fourth power of x, and we have to basically write it in the first powers of cosine of multiple angles. So again, it's cosine of multiple angles. So let's go ahead and take a look at this example over here. So this was number 4. So just like we did in example 4, that's the same thing we're going to do here. We are going to rewrite this as tangent squared and then the whole thing raised to the second power. Now remember, you are using the power reducing formula here, so we'll be using this one over here, 1 minus cosine 2u over 1 plus cosine of 2u, right? So let's rewrite this guy as 1 plus, sorry, minus on the top, 1 minus cosine of 2x over 1 plus cosine of 2x, and of course this whole thing is still raised to the second power. Now we will need to use FOIL on both our numerator and denominator, so if it helps you, I don't know, keep doing that. It should be 1 minus cosine of 2x, so that's going to be raised to the second power, and same thing for the denominator. So you're going to do FOIL on both numerator and denominator. So if you want to take a couple minutes and go ahead and do that, you can. But basically after we do our FOIL, you are going to end up getting 1 minus 2 times cosine of 2x plus cosine squared of 2x for your numerator, and 1 plus 2 times cosine of 2x plus cosine squared of 2x. Now, many of you may be tempted to cancel out some of these terms because you think they are similar on the numerator and denominator. Unfortunately, you cannot do that because these are all part of the same expression, so they are all connected to each other. So you cannot cancel anything from the numerator and denominator no matter how much you would want to. Okay, so just be careful about that. Now again, we are going to be taking these terms here, cosine squared of 2x and cosine squared of 2x, and we will be using these power reducing formulas again for those expressions. So cosine squared of u, and we have cosine squared of 2x. So because we have a 2x in here and you only have a single angle in here, what's going to happen is because of that cosine squared of 2x, this formula will actually change into 1 plus cosine, and since you do 2 times u, this will become 2 times 2x. So that actually ends up becoming 1 plus cosine of 4x over 2. Okay, so because of this extra 2, you're going to have an extra 2 in there, which will end up making this a cosine of 4x. Okay, so this guy will now become 1 minus 2 cosine of 2x. This part of course stays the same, just that last term will now become 1 plus cosine of 4x divided by 2. This is on our numerator. And then 1 plus 2 times cosine of 2x. This part stays the same. And this will become, again, 1 plus cosine of 4x divided by 2. Okay? Alrighty. Now let's see how we can clean this up. So basically, since you have a denominator of 2 over here and we have a denominator of 2 over here, these numbers, we do want to try and get rid of those denominators. So what's going to happen is we're actually going to multiply our numerator by 2, and we're going to multiply our denominator by 2, which means each of these terms. So this guy here gets multiplied by 2, he gets multiplied by 2, and then of course this whole fraction gets multiplied by 2. Same thing on the denominator. Each of these terms will get multiplied by 2. So what will happen? 2 times 1 will become 2, minus 2 times cosine of 2x multiplied with 2 will end up becoming 4 cosine of 2x, plus over here with the fraction where you have 1 plus cosine of 4x divided by 2, this 2 will cancel out with this 2 over here. So these guys will end up becoming just 1 plus cosine of 4x. So that's how we get rid of that 2 from our numerator. And then in our denominator, we're also doing 1 times 2, which will be 2, plus 2 cosine of 2x multiplied by 2. So 2 times 2 will become 4. Cosine of 2x will of course stay as it is. And then again, this 2 in the denominator will cancel out with this 2 in the numerator. And you will end up getting, in the denominator itself. And these ones will end up getting 1 plus cosine of 4x. So just remember, you are still having to distribute this 2 with all the terms. It's not just canceling out with that last term. So don't forget to distribute that 2 with all the terms, okay? And at this point, we can go ahead and combine our like terms. And your like terms will, of course, be the 2 and the 1 here, the 2 and the 1 here. Now, your cosine functions are not going to combine because they are cosine of 2x and cosine of 4x. I'm going to take this cosine of 4x, bring it to the front since he's the largest value. Then I have minus 4 cosine of 2x, so bring that in the middle. And then 2 plus 1 will give us 3. Denominator, again, cosine of 4x, I'm going to bring that to the front. Plus 4 cosine of 2x will go in the middle. 2 plus 1 is 3. I'm going to put that at the end. Again, guys, you cannot cancel out any thing between the numerator and denominator because that numerator is one whole expression, the denominator is one whole expression, so we cannot separate those and cancel anything out. So you will have to leave your answer as it is And so it's not a pretty answer, but you know, they are cosine functions of multiple angles, which is what they were asking us to rewrite it as, and we have. Okay, so that was our problem number 4. Now we are getting into half angle formulas. So they're talking about how you can derive some useful alternative forms of the power reducing formulas if you replace u with u over 2. So basically you're just replacing your angle u with a half angle u over 2, and that's why we call these guys the half angle formulas. Now you will notice for our sine and cosine functions you have these plus or minus in the front. So that's actually going to depend on what quadrant your angle u over 2 lies into. So if they're in quadrant 1, both angles are positive. If they're in quadrant 2, then cosine is negative, sine is positive. Quadrant 3, both angles are negative, and then of course quadrant 4, cosine is positive, sine is negative. So that's why they're putting the signs in there, but it's not always going to come in into play depending on what quadrant you are looking at. And then there are actually 2 different ways that you can write the tangent for u over 2. So you can write it this way or this way, and again it will just depend on how you want to simplify your expression, and based on that you can choose which one you want to do. Okay, and just looking at that remark, they are saying to find the exact value of a trigonometric function with an angle measurement in degrees, minutes, and seconds form. By using the half angle formula, you will actually need to first convert your angle into decimal form, and then the answer that you get, you're going to multiply that answer by 2. Okay, so if you come across your angles given to you in degrees, minutes, and seconds, then remember this little remark over here. Okay, so let's see how we can use these half angle formulas. They're asking us to find the exact value of sine of 105 degrees. So they are saying basically 105 degrees is half of 210 degrees, or basically you can think of 210 degrees being double of the 105. So they're saying using the half angle formula for sine over u over 2, you can actually rewrite this as sine of 105. So you can see how here you have sine of u over 2, but this is just sine of u. So that's why you need to double whatever angle you have here. So sine of u over 2 will become cosine of u. Cosine of u over 2 will become cosine of u. Same thing here, tangent of u over 2 becomes cosine or sine of u. So you have to double your angles anyway. So that's where that cosine of 210 is coming from. And then of course you can use your unit circle for cosine of 210. So your cosine of 210, this is the angle for 210, and cosine of 210 is negative square root of 3 over 2. Sorry. And so negative times negative is making this guy into a positive, and then you can see how they simplified it. Now, since they are talking about an exact value, we leave our angle in this form. You're not going to do a decimal approximation. But if you just wanted to verify your answer, take this, put it in your calculator, see what decimal answer you're coming with. Look at sine of 105 degrees again in your calculator, and you should see both of them will have the same decimal approximation. So this is just a way to check your answer, but you are going to leave your final answer in this form. Okay? And then of course they are telling us that sine of 105 degrees is going to end up being in quadrant 2, because of course you know quadrant 2 is where your angles are between 90 degrees and 180 degrees. So since this is a quadrant 2 angle, our sine function is going to be positive, so that's why this final answer comes out to be positive. Okay? Now we are asked to find the exact value for cosine of 105 degrees, and again 105 degrees is a quadrant 2 angle, which means our cosine is going to be a negative answer, right? Because cosine is negative in quadrant 2. So let's take a look at how we can simplify this guy over here. So again, remember, we are going to be using this formula right over here, the half angle formula for cosine of u over 2. So that's positive or negative 1 plus cosine of u divided by 2, and that's under your square root. So cosine of u over 2 is plus or minus square root of 1 plus cosine of u over 2. So like I said, since this is a quadrant 2 angle, cosine of theta is going to be negative. Okay, so cosine of 105 degrees, we know it's going to be negative, so I'm going to keep that negative sign in the front. And then 1 plus, so you take your 105 degrees multiplied by 2, and you get your 210 degrees. So that's going to be our u angle, and that's going to be, cosine of 210 degrees divided by 2. Okay, and then again keeping that negative sign in the front, we have 1 plus, again you guys, we are going back to that same 210 degree angle, so our cosine value is square root of negative 3 over 2, so this will be square root, sorry, not square root of negative 3, negative square root of 3 over 2, and then we still have a 2 on the bottom, so you can write this as plus or minus will be minus square root of 3 over 2, the whole thing divided by 2. Now if you wanted to get rid of your fraction over here, what you can do is again multiply both numerator and denominator by 2. So this 2 will get multiplied in this one, this 2 gets multiplied into this one, so you would end up again negative on the outside. 2 times 1 is 2, minus, when you multiply square root of 3 over 2 with this 2, your square root of, 2 and 2 will cancel out, leaving you with just minus square root of 3, and then on the denominator 2 times 2 will actually end up becoming 4. And then there's not much we can do at this point, but do just a little bit of simplification. So again, minus on the outside, you can have 2 minus square root of 3 on the top, square root of 4 on the bottom, right? And since it's square root of 4, you know that can be simplified. So 2 minus square root of 3 on the top, and of course all of that is inside the radical, and square root of 4 will end up becoming 2. Okay, and again that will be a negative angle because it's a quadrant 2. 105 is a quadrant 2 angle. So it takes a little, just be careful. Take each step slowly and you will be able to go ahead and simplify these examples, or at least find their exact value like we were doing here in this example. Okay, so this guy was problem number 5. There we go. So the next one we are looking at is 6 here, talking about solving a trigonometric equation. They are saying find all the solutions in the interval 0 to 2 pi for 1 plus cosine squared of x equals 2 times cosine squared of x over 2. So of course with cosine squared of x over 2, this part here we are replacing it with our half angle. formula over here, right? So we're making that substitution, and then basically when you take a square and a square root, of course your square cancels out your square root, right? And once you get rid of the square root, then actually this 2 on the denominator will cancel out this 2 on the outside, and that's why you are left with 1 plus cosine of x. Now that square also got rid of the negative sign here, because when you do negative times negative, you end up getting positive, right? So that's where those plus and minus signs disappear, because of course positive times positive is a positive. So it was just the negative that square ends up getting rid of the negative also. And then of course you can go ahead and bring these terms to the left hand side. So you can subtract the 1, you can subtract the cosine of x. So bring everything on the left hand side, the ones will cancel out. You factor your cosine of x, and you end up getting cosine of x times cosine of x minus 1. Set each one of those equal to 0, and then you can figure out what your x values are going to be. And remember, they said specifically in the interval from 0 to 2 pi, so we don't have to do the general form here. And again, they're just verifying by showing you the graph of the original equation that we were given, and basically they are saying you can verify these x values by looking at their decimal approximation. So we have x equals 0, which will be this point right over here. X equals 1.571, which is approximately pi halves. So that's going to be this point right here. And then x is approximately equal to 4.712, which is approximately equal to 3 pi halves. And that's going to be this point right over here. So they're just showing how you can verify where your function is going to be crossing the x-axis at, or where your x-intercepts are in this interval from 0 to 2 pi. Again, guys, we are not doing the graphical solution, so don't worry about that. Okay, so for example 6, we are given, we have to find all the solutions for cosine squared of x equals sine squared of x over 2. And again, we're doing this in the interval from 0 to 2 pi. Okay, so let's take a look at this example over here. So we're of course going to start with the half angle formula and go ahead and substitute the right hand side. We're keeping our left hand side as it is, and of course, since we don't know which quadrant these angles are going to be in, we're going to keep our positive and negative sign. So sine of x over 2 will become 1 minus cosine of x over 2. Now since this is sine squared, we also need to put that squared on here, right? And then just to show you guys, this was that half angle formula that we ended up using over here. So sine of u over 2 is plus or minus square root of 1 minus cosine of u over 2. And then since we had the square, we needed to include the square on that. So two things are going to happen here. That square is going to take our positive and negative sign and make both of them into a positive sign. So we won't have to write a sign down here anymore. And then additionally, this square will also cancel out the square root. So positive times positive is becoming a positive. Negative times negative is also becoming a positive. And the square root is canceling out the square. So you will end up getting just 1 minus cosine of x over 2 on the right hand side. Okay, and then basically the next thing we want to do is get rid of that denominator of 2. So we're basically going to go ahead and multiply both sides of our equation by 2, get rid of that denominator. On the left hand side, you'll end up getting 2 times cosine squared of x, and then 1 minus cosine of x will be left behind on the right hand side, right? So now to solve this, of course, we want to bring everything else to, I guess, the left hand side. So we'll go ahead and start by adding cosine of x and then subtracting the 1 also. So these guys will cancel out. And let's see, we will be left behind with 2 times cosine squared of x plus cosine of x minus 1, and then of course everything becomes 0 on the right hand side. So if you notice this again, this is in the form of our quadratic function. So if you again think of u as being our cosine of x function, you again have 2u squared plus u minus 1. So this will again factor out into 2u minus 1 and u plus 1 for the other one. So bringing that back into our function will actually end up becoming 2 cosine of x minus 1 cosine of x plus 1 equal to 0. And this is actually the same thing we had in, I believe it was example 1. So you will notice we're going to get actually the same type of examples there. So cosine of x will be negative 1. And then here we add 1. Then divide by 2. And we end up getting 1/2. So these guys will cancel out. So for these guys, where you have positive 1/2, not that one. You can see it's going to be those same values. You had cosine of x equal to 1/2 at pi over 3, and cosine of x equals 1/2 at 5 pi over 3. And then for this side, cosine of x equals negative 1, of course, happens at pi. Okay, and like they said, they only want the solutions in the interval from 0 to 2 pi. Our x values are going to be pi over 3, 5 pi over 3, and x equals pi. That's it. So this here will be our solution set for problem number 6. So you can see once you actually figure out which formula to use and how to break it down, it really is not quite as bad. So again, look through this example, and if you have any questions, definitely please let me know. So that one was example number 6. Okay, now we are getting into our product to sum and sum to product formulas. So as it's telling us here, you can use the product to sum formulas and prove that they are going to be true by actually looking at the sum and difference formulas from section 2.4. So here again are our product to sum formulas here. So you can see we were actually originally given a product of sine of u multiplied by sine of v. And now here we are doing a plus or a minus on our functions here. So you can see all 4 of those functions over here. I'm not going to go through them, but let's see how we can actually use these formulas. So they're saying product to sum formulas again are used in calculus, where you could be given the product of sine and cosines with 2 different angles, right? Because you have angle U and angle V. So let's see how we can write these guys down. So they're saying rewrite the product of cosine of 5x times sine of 4x as a sum or a difference. Of course, this is cosine multiplied by sine. So you are actually looking at this last one over here, cosine of u times sine of v. So that's cosine of 5x, sine of 4x, which gives you 1/2, sine of 5x plus 4x, which of course will add up to give you sine of 9x. And then here you have minus sine of 5x minus 4x, which will of course just end up giving you 1x or just x. And then what they did was they took this 1/2 and distributed it with both the signs. And so you can see once you're just translating that formula, it actually cleans up pretty quickly, and you have 1/2 sine of 9x minus 1/2 sine of x as your final answer. So something very similar in our example, we are looking at sine of 5x multiplied with cosine of 3x. So sine of 5x multiplied with cosine of 3x is going to be this third formula over here that we are going to be using. So let's go ahead and take a look at this guy. So this one is using the rule sine of u multiplied by cosine of v, which is 1/2 sine of u plus v plus sine of u minus v, right? So that's the rule that we are using over here. So let's translate that into our problem. So this will become 1/2 sine of 5x plus 3x plus sine of 5x minus 3x. Okay? Again, that 1/2 is staying on the outside. We have sine of 5x plus 3x will of course become 8x plus sine of 5x minus 3x, which will of course become 2x. And then all we have to do is distribute this minus sign inside our brackets, which will end up giving us 1/2 sine of 8x plus 1/2 sine of 2x, and that's it. That's all you gotta do. Okay, so that's how we simplify or rewrite, I guess in this case, problem number 7. Okay, by using those product to sum rules. Now, sometimes we may have to reverse that procedure. So instead of going from product to sum, we may need to rewrite sums as products, right? So go in the other direction. So this is where we're getting our sum to product rule. So you can see these guys were either sum or differences, and now they are going to be products on the right hand side because you're multiplying sine with the cosine function, or cosine with cosine, or sine with sine, right? Again, you have proofs for these in your textbook if you just wanted to see how they came up with this. But let's see how to put this rule into use. So we are given cosine of 195 plus cosine of 105, and they're asking us to find the exact value. So since this is cosine plus cosine, you are actually looking at the third rule over here. Okay, so we've got 2 times cosine of 195 plus 105 divided by 2, and that whole thing is being multiplied by cosine of 195 minus 105 divided by 2. So 195 plus 105 will of course give you 300 degrees. 300 degrees divided by 2 gives you the 150 over here. And then 195 minus 105 of course gives you 90 degrees. And then 90 degrees divided by 2 gives you the 45 degrees. So cosine of 150 and cosine of 45, we are going to go to our unit circle. So 150 is right here. Cosine of 150 is negative square root of 3 over 2. And cosine of 45 is of course square root of 2 over 2. So that's where, oops, wrong place. That's where they are coming up with these numbers from. You can go ahead and simplify your answer, and you of course end up getting negative square root of 6 over 6, which basically essentially you can think of this 2 canceling out this 2 on the denominator. You're multiplying negative square root of 3 with square root of 2, which is giving you square root of 6, and then 2 on the denominator will end up staying behind. Okay, so our problem number 8 is asking us to find the exact value for sine of 195 plus sine of 105. So we're adding sine with sine function. So that's going to be this first rule over here. So you can see this is going to be a combination of sine and cosine when we do the product on the right hand side. So let's take a look at number 8 for us. So again, let me write that rule down. We are doing sine of u plus sine of v. So that's going to be 2 times sine of u plus, sine of u plus v over 2. And of course, the second part was going to be cosine of u minus v over 2. Okay? So that's kind of what that guy ends up looking like. So let's put this together here. Okay, so 2 times sine of 195 plus 105 divided by 2, and we're multiplying this by cosine of 195 minus 105 divided by 2. So that will give you sine of 300 degrees divided by 2, cosine of 90 degrees divided by 2. And you of course don't have to break it down like I am. You can go directly to the final answer, which would be sine of 150 degrees cosine of 45 degrees, right? Okay, so sine of 150 degrees is going to be 1/2. Cosine of 45 degrees, of course, is square root of 2 over 2. So this 2 will stay here, and then this guy will become 1/2. This guy will become square root of 2 over 2. So if you want, you can think of this guy as being over 1. So this 2 will cancel out with this 2. So basically it looks like you are left behind with only square root of 2 over 2. And that's going to be your exact answer for problem number 8. There you go. Okay. So this one was problem number 8. So we're getting close here towards the end. Now this example here is again talking about solving and finding the answer for sine of 5x plus sine of 3x equal to 0. So this is adding sine with sine function. So it's actually the same rule that we did here, which is your rule number 1 over here. So that's the same rule we are using. So that's going to give you 2 times sine of 5x plus 3x over 2, cosine of 5x minus 3x over 2, which then becomes 2 times sine of 4x cosine of x equals 0. And what they are basically saying is take your factor of 2 times sine of 4x, set it equal to 0. Take your cosine of x, set it equal to 0. Find your solution. So if you took 2 times sine of 4x and set it equal to 0, we'd of course start by dividing by 2 first, and you would get sine of 4x equals 0. And sine is 0 at, well, angle 0. And sine is of course also 0 at pi. So those are the two locations where your sine function is going to be 0 at. Okay, so we will say then 4x is going to be at 0 and pi. And if we divide both sides by 4, you will of course end up getting x equals 0 and x equals pi over 4. And of course, if you keep going in oscillations or coterminal, you can actually prove for all of these other angles also. So basically we are saying that every 45 degrees you're actually basically going to be seeing this function being true and those will be basically, you can kind of show that cosine of x equals 0 does not give you any additional solutions either. So since they're not adding anything else to the solutions, we can actually say that our solutions, all of these solutions, are actually of the form x equals n times pi over 4, where of course your n will be an integer, and then you can of course show this graphically also, and you can kind of see all of these places where you are going to have your x-intercepts are all going to be in increments of that pi over 4. Okay, so these are all multiples of pi over 4 over here. Okay, so our example is going to be somewhat similar to this one, and we are given sine of 4x minus sine of 2x equals 0. So let's see how we can go about taking care of this guy. So let's start out, and of course this is sine of 4x minus sine of 2x, right? So this is going to be our, oh, I think I went up too far. There we go. The second function over here. So sine of u minus sine of v. Okay. So let's go ahead and write that rule down here. Sine of u minus sine of v is going to be 2 times cosine of u plus v over 2 multiplied by sine of u minus v over 2. Okay? So this will become 2 times, oh, that should be cosine at the front, 2 times cosine of 4x plus 2x over 2 multiplied by sine of 4x minus 2x over 2, and of course this is still equal to 0, so we will end up getting 2 times cosine of course 2x plus 4x will be 6x over 2, sine of 4x minus 2x will be 2x over 2, which will end up giving you 2 times cosine of 3x times sine of basically just x, right? Because these 2 and 2 will cancel out, this 2 will go into 6 3 times, so you can go ahead and simplify those. Now the next thing we're actually going to do, and we could have done this in example 9 also, is we can go ahead and divide both sides by 2, because that's really not helping us as part of our answer. So you will be left behind with cosine of 3x sine of x equal 0, and then of course we need to set each one of these functions equal to 0 and find what answers we can. So let's take our cosine of 3x, set it equal to 0, or our sine of x and set it equal to 0. Okay, so let's see what can we get for cosine of 3x equal to 0. So cosine is equal to 0 at pi halves, right? And it's equal to 0 at 3 pi halves. So those are the two angles where our cosine function is equal to 0. So we can say 3x would be equal to 0 at pi halves, and 3x would be equal to 0 at 3 pi halves. Okay, so we'll do the same kind of thing here for our sine function. So now we have to find for which values of x is our sine function going to be equal to 0. And of course our sine function is equal to 0 at angle 0 and of course at angle pi. So for this guy our x will be 0 and x will be pi. Okay. Now they're asking us to solve this equation in general terms, which means we are not doing this just for the interval 0 to 2 pi. So that means each one of these answers has to add up with 2 and pi, because that's the period for sine and cosine function. So that would be 3x equals pi halves plus 2n pi, and then of course 3x equals 3 pi halves plus 2n pi. And this is of course our general form. Same thing over here for the general form coming from the sine function. We would have x equals 0 plus 2n pi, and x equals pi plus 2n pi, right? Okay, so now what we're going to have to do is basically get our x by itself, which is going to happen on the left hand side here. So we are going to take each of these equations and divide it by 3. Dividing by 3 is the same thing as multiplying by 1/3, right? So this 3 and 3 will cancel out, getting us x by itself. And then for the other terms, for that first one, you will have x equals pi halves multiplied by 1/3 plus 2n pi multiplied by 1/3, which will of course end up giving you pi over 6 plus 2n pi over 3, right? For that second one, you will end up getting x equals 3 pi halves times 1/3 plus 2n pi again times 1/3, which will end up giving us, let's see here, this 3 and 3 can actually cancel each other out, giving us pi halves on this side and then plus 2n pi over 3 on the other side. And let's see, for our right hand side with the sine function, you can also clean that up because you will get x equals 2n pi from the first one and x equals pi plus 2n pi. But if you think about it, these are all basically just multiples of n pi, right? Because if I make my n function here a 0, then I just get pi from here. If I make my n function, well, I can actually make it a negative 1, and I can end up getting different variations because of course n is going to be your integer value. So you can kind of see you will actually go through all iterations of 1 pi, 2 pi, 3 pi, 4 pi, and then negative 1 pi, negative 2 pi, negative 3 pi as you go forward. So all of these can actually just become multiples of n pi. So you can actually say that x just equals n pi in this case. So we can actually clean up these answers quite a bit after you have solved them. So we can say our general solutions can actually be x equals pi over 6 plus 2/3 n pi from that first one. You can have x equals pi halves plus again 2/3 n pi, and our last one will be x equals n pi. So these will be our general solutions for this example number 9 over here. Okay? Alrighty, very nice. So this one was problem number 9. And so the very last thing we actually want to talk about is this application problem over here. So they're saying ignoring air resistance, so we don't want to think about how the air resistance may be slowing down our object. They are saying the range of a projectile fired at an angle of theta with the horizontal. So basically they're saying this projectile is traveling along a horizontal distance, and with an initial velocity of v sub 0 feet per second, the range of our projectile is given by this equation. So you have 1 over 16 v sub 0 squared multiplied with sine of theta times cosine of theta, where r is going to be your horizontal distance in feet that projectile is going to travel. So basically you can think of this same example as, what if a football player was going to kick a football from the ground level and he has an initial velocity of 80 feet per second. So they want to know two things here. First thing, they're asking us to rewrite the projectile motion model in terms of the first power of the sine of a multiple angle. So they actually want us to rewrite that equation using the first power of a sine of a multiple angle. So remember, sine of a multiple angle is going to be in terms of sine of k times u. And then of course part B, they're saying at what angle must the player kick the football so that the football will travel 200 feet. So they just want to know what that theta value should be if that distance r is going to be 200 feet. So let's take a look at that first portion over here. They're asking us to rewrite this sine of theta, cosine of theta as just a multiple angle for the sine function. So they are actually using the double angle formula here, but what they have done is we don't have that multiplied by 2 over here, right? So since we're multiplying by 2 on the numerator, you also multiply by 2 on the denominator to balance it out, right? So basically you're multiplying this whole, if you think about it, they're multiplying this whole fraction or this model here by 2 times 2. So this 2 times 2 on the bottom with the 16 times 2 ends up becoming your 32. And then this numerator of 2 is going in with your sine of theta and cosine of theta. So that's how we're able to rewrite this guy as sine of 2 theta. So it ends up becoming 1 over 32 v sub 0 squared of sine of 2 theta. And then they're asking us at what angle can we get a distance of 200 feet. So 200 feet for our r. They of course told us that the initial velocity was 80 feet per second. So that's where this 80 is coming from. And then you're just going through your calculations, get sine theta by itself, and looks like you end up getting sine theta. Sine of 2 theta equals 1, and of course sine is going to equal 1 at this angle of pi halves, right? So that's where they are getting this 2 theta equals pi halves from. Divide both sides by 2, you end up getting theta equals pi over 4, or 45-degree angle. So they're saying if the football player takes this football at an angle of 45 degrees, that ball will travel 200 feet. So initial velocity of 80 feet per second at an angle of 45 degrees will give you a distance traveled of 200 feet. Okay? So we're using that same example for our problem over here, but this time they want to know for what angle is the horizontal distance the football travels maximum. So basically, what angle should the ball be kicked at so that you get the maximum distance traveled by the football. So let's go ahead and take a look at this example over here. Okay, so let's see. Our formula that's given to us is r equals 1 over 16 v sub 0 squared sine theta cosine theta, and then of course they are telling us that the initial velocity the ball was kicked at was 80 feet per second. Okay. Now, since they are talking about finding that maximum distance the ball travels, we will also go ahead and rewrite our angle here actually in the sine of a multiple angle term. So we'll go ahead and multiply both numerator and denominator by 2. So you will end up getting 1 over 32 just like we had in the example 10. And then this will become 2 times sine theta cosine theta. And this one here we can write using our double angle formula. So you end up getting 1 over 32 v sub 0 squared times sine of 2 theta. So we're bringing in that double angle calculation in here. Okay, now to talk about the maximum distance traveled, we're going to go ahead and put in our initial velocity in here, which is 80 feet per second. And that will, of course, end up giving us 80 times 80 is 6,400. So that will be 6,400 over 32 and sine of 2 theta. And of course, this is all going to clean up into 32. Will go into 6,400 200 times. And you get sine of 2 theta. But now we still have to talk about how can we find that angle where we get the maximum value from. So, this is a basic sine function, and the idea is you have to graph this sine function to actually see where it's going to reach that maximum height. So let's go ahead and take a look at what that will look like. Okay guys, so this is again from our website for the author of this textbook, larsonprecalculus.com. So as you can see, graphing this function by hand is not going to be an easy process. So they've used a graphing calculator over here, and basically you can see as you travel along the path of the sine function, your maximum value is of course going to be when we reach that height of 200 feet, or in this case, of course, we're talking horizontal distance, but on the graph, it's going to look like your maximum height. And so that's going to happen actually when you get to an x value of approximately 45 degrees. So even in this case, we are saying that you are going to get to that maximum distance at an angle of 45 degrees. And that's actually what you also did in example 10. So it's at 45 degrees where the football player, he or she, I guess, the ball reaches a distance of 200 feet. So even when you do it in this generic terms, it looks like you are still looking at 45 degrees as your angle. So this is going to happen when theta is approximately equal to 45 degrees. We can say the football travels a maximum distance. Okay, so that's going to happen at the 45 degree angle. Alrighty, so this was, I believe, our last example here for section 2.5. So again, remember guys, this is the last section for chapter 2. If you have any questions, please let me know, and we'll talk about this in class. So have a wonderful day, be careful, and see you next time. Bye-bye.